NASA is tracking an asteroid heading straight past Earth in less than 48 hours. They know exactly where it's going. What they don't know, and this is the part nobody's talking about, is how big it is. 2026 DX6 will pass at just 2 lunar distances, 770,000 kilometers. Now you might think that's far, but in space terms that's very, very close. Close enough that planetary defense teams are paying serious attention. And right now it could be the size of a bus or the size of something capable of leveling an entire city. We genuinely do not know. And to make it worse, a solar storm is arriving the same weekend, degrading the exact instruments we need to find that answer. Stay with me until the end, because what this situation actually reveals about our planetary defense system is far more unsettling than the asteroid itself. If this has you hooked, hit subscribe so you do not miss what comes next as new data continues streaming in. Drop a comment telling me where you are watching from right now and tell me, does it bother you that something this close will pass without a public size estimate? And if you want to help the Skylab grow, share this one. You are the reason we keep digging for stories like this. Now, let's get into it. Something is coming, not in the way that phrase usually gets weaponized by headlines trying to sell you panic. Not a movie trailer, not a conspiracy thread. This is a verified, tracked, officially catalogued object, and it has a name: 2026 DX6. And as of this recording, it is scheduled to fly past Earth on March 2nd at a distance of approximately 2 lunar distances, roughly 770,000 kilometers from the surface of the planet you are currently sitting on. Now, before your heart rate does anything dramatic, let me be precise about something, because precision is the entire point of this video. This is not an impact scenario. The current orbital solutions, the math that real scientists have run on real telescopes using real data, show a safe passage. 2026 DX6 is going to zip past us and continue on its way through the solar system. And the official probability of impact is not a source of genuine concern right now. But here is the thing. Here is the part that actually matters. We do not know how big it is. That is not a rhetorical device. That is the operational reality of this specific moment. As of the data currently available, there is no confirmed diameter estimate for 2026 DX6. And that single missing number, that one gap in our knowledge, is what makes the next 48 hours genuinely interesting to anyone paying attention to planetary defense. Let me walk you through why. When we talk about an asteroid passing at 2 lunar distances, most people hear 2 moons away and shrug. That sounds far. And in human terms, it is. But in the terms that planetary defense scientists use to categorize close approaches, 2 lunar distances is operationally close. It sits inside a threshold that triggers enhanced monitoring, additional observation campaigns, and a whole cascade of scientific attention. The moon is about 384,000 kilometers from Earth. 2 lunar distances is roughly 770,000 kilometers. For reference, that is about twice the distance to the moon and about 0.5% of the distance to the sun. In orbital mechanics terms, that is a whisker. Now, the trajectory is not the mystery here. We know where it is going. What we do not know is what it is made of, how large it actually is, and therefore how much energy it would theoretically carry if, in some alternate universe where the math worked out differently, it were on a collision course instead of a close pass. And that matters because the energy scaling on an asteroid impact is not linear. It is cubic, diameter cubed, which means small differences in size translate into enormous differences in destructive potential. Think about it this way. An object around 10 meters across, roughly the size of a large bus, would produce a brilliant fireball if it entered the atmosphere. It would likely detonate in an airburst well above the ground. Spectacular? Possibly startling, but survivable. Scale that up to 30 to 50 meters, the size of a small office building, and you are now in Chelyabinsk territory. That was the object that exploded over Russia in 2013, injured over 1,500 people, and shattered windows across an entire region without a single piece of significant mass reaching the ground. And if 2026 DX6 turns out to be somewhere in the 80 to 100 meter range, now you are in the neighborhood of Tunguska. an airburst capable of flattening everything within a radius of dozens of kilometers. A city killer that arrives without a crater. We don't know which of those scenarios fits this rock. It could be 10 meters, it could be larger. Right now, the honest answer is, we are working on it. What we do have is a 48-hour refinement window. As this object draws closer to Earth, its angular motion across the sky increases dramatically, and every new observation tightens the orbital solution. Astronomers call this arc compression, the rapid reduction in positional uncertainty that happens when an object is near its closest approach. The uncertainty does not vanish, but it shrinks fast. The trajectory is getting cleaner by the hour. But the trajectory was never really the question. The mass is. And what makes this case genuinely unusual is not the distance, and it is not even the size uncertainty on its own. It is the timing. Because something else is happening this same weekend, something 93 million miles away, that is about to make an already complicated picture considerably harder to read. If you are wondering how a planet-monitoring civilization with space telescopes and radar arrays and orbital supercomputers can track something closely enough to know exactly when it will pass Earth and yet still not know how big it is, that is a completely fair question. And the answer tells you a lot about how planetary defense actually works versus how most people imagine it works. 2026 DX6 was almost certainly discovered recently, through one of the automated survey programs that sweep the sky for exactly these kinds of objects. Systems like the Catalina Sky Survey, Pan-STARRS or the Atlas network are constantly scanning, comparing nightly images, flagging anything that moves against the fixed background of stars. When a new dot appears and moves in a way that suggests a solar orbit crossing Earth's path, an alert goes out. That alert triggers follow-up. And from the moment of discovery, astronomers begin building what is called an observation arc, a sequence of position measurements spread across time that allows orbital mechanics software to calculate where the object has been and where it is going. Here is the problem. For a newly discovered object, that arc is short, sometimes hours, sometimes a couple of days, and a short arc means wide uncertainty bars. The orbit might be well constrained enough to rule out imminent impact, but that is a very different thing from knowing the object's physical properties. Orbital mechanics and physical characterization are two separate problems, and solving one does not automatically solve the other. Size, specifically, is where it gets complicated. You might assume that brightness tells you size, brighter object, bigger rock, right? Not quite. An asteroid's observed brightness depends on two things: its size and its reflectivity, which astronomers call albedo. A large dark rock and a small bright rock can appear identical through a telescope. A carbonaceous asteroid, dark, primitive, absorbing most of the light that hits it, might have an albedo of around 3 to 5%. A bright stony or metallic asteroid might reflect 20 to 30% of incoming sunlight. Run that through the math and you get a size estimate that varies by a factor of 3 to 5 times, depending on which kind of rock you are looking at. 3 to 5 times. That is the difference between a bus and an office building. There is also the issue of phase angle. When an asteroid is approaching Earth, especially from certain directions, it can be partially backlit by the sun. The geometry of illumination affects its apparent brightness in ways that are hard to fully correct without additional observations from multiple angles over time. Early in a short arc discovery, those corrections are imprecise. You're essentially reading a dimmer switch that is also being twisted by someone else. So why not use radar? Radar is the gold standard for physical characterization. Facilities like the Goldstone Solar System radar or the Arecibo successor systems can bounce radio waves off an asteroid and get back not just precise distance and velocity data, but in some cases actual shape and size constraints from the radar cross-section. It sounds like the obvious answer. And it often is. But radar characterization has real constraints. The geometry has to work, the object needs to be at the right distance and declination for a given antenna to reach it. Scheduling is competitive because these are shared research facilities with multiple scientific priorities, and signal-to-noise ratios at even relatively close distances can be challenging for a small, fast-moving object that has only recently been discovered. This is not a failure of the system, it is the system operating as designed under real-world constraints. But it does mean that for the next 48 hours, 2026 DX6 remains partially described, its trajectory known, its mass an open question. And what makes this particular observation window even more pressured than usual is that the Sun is not cooperating right now, not even a little bit. Right around the same weekend that 2026 DX6 makes its closest approach to Earth, a coronal mass ejection, a CME, is forecast to arrive in our neighborhood. And before you file that under interesting coincidence, let me explain why it matters to the story we are telling about an asteroid we cannot yet measure. A coronal mass ejection is an enormous eruption of magnetized plasma from the Sun's outer atmosphere. When one of these plasma clouds reaches Earth, it interacts with our planet's magnetic field in ways that can trigger geomagnetic storms. These storms are graded on a scale from G1 to G5, with G1 being mild and G5 being a civilization-level event. What we are looking at this weekend is not a G5, but even a moderate geomagnetic storm creates measurable turbulence in Earth's ionosphere, the upper layer of the atmosphere that radio signals pass through on their way to and from the ground. And here is where it connects directly back to our unnamed asteroid. Radar tracking of near-Earth objects depends on radio waves traveling cleanly through that same ionosphere. When the ionosphere is disturbed by a geomagnetic storm, signal propagation degrades, the noise floor rises, measurement precision shrinks. Not catastrophically, modern tracking systems are designed with margins, but the margins tighten. And when you are already working with limited observational data on an object of unknown size, tighter margins are the last thing you want. There is also the matter of GPS timing precision. Orbital calculations depend on extremely precise timing data, and GPS signals are among the tools used in observatory synchronization. Geomagnetic storms are well documented to degrade GPS accuracy, sometimes by meters, sometimes more. In isolation, that sounds minor. In the context of characterizing a fast-moving object at close approach over a compressed time window, every precision hit compounds. This is not a catastrophe. Let me be clear about that. The tracking infrastructure will continue to function, alerts will be issued, measurements will be taken. But what the CME arrival does is function as a stress test, arriving at precisely the moment when we most need clean data on an object we least understand. The solar system is not staging this for dramatic effect, but if it were, the timing would be impeccable. Because the uncertainty about what 2026 DX6 actually is remains wide open, and the tools we most need to close that uncertainty are about to operate in degraded conditions. Which raises a question worth sitting with for a moment. If this object were larger than we suspect, not a threat during this pass, but something worth understanding deeply, would we catch that in time? Keep that question in mind, because what the orbital geometry of this specific pass reveals is more unusual than the distance alone suggests. The number 770,000 kilometers describes where 2026 DX6 will be at closest approach, but it does not describe how it will get there, or how fast, or at what angle, and those details matter enormously for understanding what this pass actually means scientifically. Near-Earth objects are generally classified by the shape and orientation of their orbits relative to Earth's path around the Sun. Apollo-type asteroids have orbits that cross Earth's orbit, with a semi-major axis larger than 1 astronomical unit. AIMA-type objects have orbits that come close to, but do not quite cross Earth's orbit. Without confirmed orbital elements published for this specific object, we stay general. But the close approach geometry alone tells us that whatever classification applies, this is an object whose path intersects the inner solar system in a way that puts it repeatedly in proximity to Earth's orbital neighborhood. At closest approach, 2026 DX6 will be moving at a velocity relative to Earth that is, depending on the specific trajectory, likely in the range of tens of thousands of kilometers per hour. That velocity combined with mass is what determines kinetic energy. And kinetic energy, not distance, not trajectory, not probability of impact, is the number that planetary defense scientists care about most when they are trying to understand what an object is capable of in the worst case. Here is a concept worth understanding called the gravitational keyhole. Around any planetary body, there are specific narrow regions of space, often just a few hundred kilometers across, where, if an asteroid passes through them during a close approach, the planet's gravity will bend the object's trajectory just enough to set it on a collision course during a future orbit. These keyholes are calculated from orbital mechanics and uncertainty ellipses, and they represent one of the more quietly alarming aspects of asteroid science. For certain well-tracked objects like Apophis, keyhole analysis was central to the risk assessment for the 2029 and 2036 close approaches. Let me be clear, no known keyhole threat is associated with 2026 DX6. The current data does not suggest it, but the concept matters here because it illustrates why even a safe pass is not simply a non-event. Scientists use something called a B-plane analysis to map out where exactly an asteroid will pass relative to Earth during a close approach. The B-plane is an imaginary flat surface perpendicular to the incoming trajectory, centered on Earth, and the B-plane uncertainty ellipse describes the statistical spread of where the closest approach point might be. Right now, that uncertainty ellipse for 2026 DX6 is relatively large because the observation arc is short and the physical properties are unconstrained. As the object approaches, every new measurement collapses that ellipse further. By the time it passes on March 2nd, the uncertainty will have shrunk to a fraction of its current size. There is also a long-term consideration for small objects, the Yarkovsky effect. Sunlight absorbed and re-emitted as heat by an asteroid applies a tiny but persistent force on the object's trajectory over years and decades. For large asteroids, this effect is negligible. For small ones, and 2026 DX6 may well be small, it can shift orbits by meaningful amounts over long time periods. Calculating Yarkovsky drift requires knowing the object's size, mass, rotation rate, and thermal properties. Without knowing the diameter, you cannot calculate the drift. Without calculating the drift, your long-term trajectory model has an unconstrained variable baked in. This is why this pass is not just a near miss to observe and forget. It is an information event. Every minute of radar time, every optical measurement, every photometric data point collected during this close approach directly improves our ability to model this object's behavior for the next decade and beyond. The asteroid is not dangerous right now, but we are establishing the foundation of knowledge that tells us whether it might ever become significant later. And here is the uncomfortable part. That knowledge-building mission is currently being conducted under pressure with degraded instruments in a compressed time window. The question of how clean that information actually is matters more than any headline has acknowledged. On June 30th, 1908, something entered Earth's atmosphere over a remote stretch of Siberian forest near the Podkamennaya Tunguska River. It never reached the ground. It detonated somewhere between 5 and 10 kilometers up, releasing energy equivalent to roughly 10 to 15 megatons of TNT, hundreds of times more powerful than the atomic bomb dropped on Hiroshima. The explosion flattened approximately 2,000 square kilometers of forest. 2,000. And because it happened over one of the most sparsely populated regions on Earth, the death toll was probably close to zero. Probably. Now move that airburst 4,000 kilometers west and put it over a major European city. The math doesn't change, only the outcome does. Most people file Tunguska as ancient history, a curiosity from a century ago when nobody was watching the sky. And then 2013 happened, and suddenly it was not ancient history anymore. On February 15, 2013, a meteor estimated at roughly 17 to 20 meters across entered the atmosphere over Chelyabinsk, Russia, traveling at approximately 60,000 kilometers per hour, and detonated in an airburst that shattered windows across 6 cities and injured over 1,500 people, almost all of them from flying glass. The object was smaller than a house. It arrived completely undetected, and it injured more people than some military strikes. This is the part of asteroid science that does not make the neat infographics about extinction-level events. The mid-sized objects, the ones too small to track reliably from survey telescopes in advance, too large to dismiss as harmless fireballs, represent the most probable damaging scenario for a human population on any given century timescale. They are common enough to be a statistical reality. They are small enough to slip through detection nets, and they deliver most of their energy in the atmosphere, where the shockwave spreads horizontally rather than cratering into the ground. Which brings us directly back to 2026 DX6. Not because it is predicted to impact, it is not. But because the uncertainty in its size means the uncertainty in its theoretical energy, yield spans a range from impressive fireball to Tunguska-class atmospheric event. That range does not vanish just because the trajectory clears Earth. It stays relevant because understanding the object matters for future tracking, and right now that understanding is incomplete. A safe pass does not answer the question of what this thing is. It just means we get to keep asking. You might be asking a reasonable question right now. With all the sky surveys running continuously, with all the computational tools we have, with the entire Space Guard effort and the Planetary Defense Coordination Office and decades of institutional investment in this problem, how does an asteroid get close enough to be within 2 lunar distances before we have a firm size on it? The answer involves several overlapping problems, none of them simple, all of them real. The most significant is geometry. Ground-based telescopes are limited in where they can look by the Sun. Objects approaching Earth from the direction of the Sun, from inside our orbit, or from low solar elongation angles, spend most of their pre-approach trajectory in daytime sky, invisible to optical surveys that only operate at night. By the time such an object has moved far enough from the Sun to be observable, it may already be days away from closest approach. This is not a gap that better cameras fix. It is a geometry problem. It requires either space-based observatories positioned where they can look toward the Sun, or fundamentally different survey strategies. There is also the matter of speed. Objects on close approach trajectories move fast relative to the background sky. Automated detection algorithms need to distinguish a moving dot from stars, artifacts, and noise across sequential images taken minutes apart. Very fast movers can sometimes slip through cadence gaps, appearing in one image but moving off-frame before the confirmation shot is taken. Survey cadence is further complicated by the Moon. During bright lunar phases, the sky background brightens significantly, reducing the sensitivity of optical telescopes to faint objects. If a discovery window coincides with full moon, the effective detection threshold gets worse precisely when you might need it most. Then there is the institutional reality. Survey telescopes are not exclusively dedicated to planetary defense. They are research facilities with competing scientific priorities, transient phenomena, galaxy surveys, variable stars, gravitational wave counterparts. Telescope time is allocated. Detection algorithms are optimized for efficiency, but not perfection. And when an object is discovered, the pipeline from detection to characterization to public alert involves multiple organizations with their own communication timescales. None of this means the system is broken. The Near-Earth Object Catalogue has grown enormously over the past 3 decades, and the detection rate of small objects has accelerated significantly with improved algorithms and wider sky coverage. We are finding more than ever before. The problem is that more than ever before is still not the same as all of them. And the ones most likely to slip through are exactly the mid-sized objects, the 20 to 100 meter class, that are too small for current surveys to find reliably at large distances, but large enough to cause serious regional damage. What is quietly unsettling is this. We are in a period of solar maximum right now, meaning the Sun is near the peak of its 11-year activity cycle. That has direct implications for the detection and characterization environment we just discussed. And understanding why requires looking at the solar cycle itself with the same level of scrutiny we have been applying to this asteroid. The Sun is not a stable, quiet furnace. It breathes. Roughly every 11 years, solar magnetic activity rises from a minimum when the Sun is relatively calm to a maximum when the surface becomes magnetically complex, sunspot numbers peak, and the frequency of solar flares and coronal mass ejections increases substantially. We are currently in solar cycle 25, and by multiple metrics, this cycle has been more active than many scientists predicted. We are near or at the peak right now. During solar maximum, the rate of significant solar flares and coronal mass ejections increases meaningfully. Some of these events are relatively minor: elevated particle flux, mild geomagnetic disturbances. Others are significant enough to affect satellites, degrade high-frequency radio communications, and create intense auroral displays at latitudes that rarely see them. We have seen multiple moderate to strong geomagnetic storms over the past year, some reaching G3 and G4 levels on the NOAA scale, creating measurable disruptions to GPS precision, radio navigation, and low Earth orbit satellite operations. This matters for our story because the observation infrastructure we rely on to characterize objects like 2026 DX6 does not exist in a vacuum. It exists in the same electromagnetic environment being churned up by solar maximum activity. Ionospheric turbulence does not care that we have an important asteroid to measure. Elevated particle flux does not pause while ground stations recalibrate. The same solar energy that makes auroras beautiful makes precision measurement harder. And here is the part worth sitting with quietly. Solar maximum is also when the background noise in near-Earth space, the particle environment through which optical sensors look and radar signals travel, is at its most disruptive. We are trying to get the clearest possible read on an object we have just discovered, using instruments operating in their most challenging seasonal environment on a compressed timeline. Solar activity does not alter the asteroid's path in any short-term sense, but it absolutely tightens the measurement tolerances at precisely the moment we need them widest. And for 2026 DX6, that coincidence could not be worse timed. Let us talk about what actually happens when scientists try to get precise measurements of a fast-moving asteroid in conditions like these, because the picture is more complicated and more interesting than most coverage acknowledges. Radar ranging works by transmitting a powerful radio signal toward an asteroid and measuring the return. The round-trip travel time of the signal gives you precise distance. The Doppler shift, the change in frequency caused by relative motion, gives you precise velocity. And the strength and shape of the return signal can, in favorable cases, constrain the object's size via radar cross-section. It is extraordinarily powerful. When it works cleanly, radar turns an orbit uncertainty ellipse into something almost vanishingly small within hours. But the signal has to travel through Earth's ionosphere twice, once on the way out, once on the way back. Under normal conditions, the ionosphere introduces predictable delays that can be modeled and corrected. Under geomagnetically disturbed conditions, those delays become irregular and harder to model. The ionosphere during a geomagnetic storm is not a smooth, stable layer. It is a turbulent, variable medium that scatters and delays radio signals in ways that introduce noise into your measurement. The more noise, the larger your error bars. The larger your error bars, the less you have actually constrained. Optical observations face a different but related challenge. Space-based sensors, some of which monitor near-Earth objects continuously, are exposed to elevated charge particle flux during solar storms. Individual pixels in charge-coupled device detectors can be struck by energetic particles, creating false signals that require filtering. Calibration routines that assume a baseline noise level may perform differently when that baseline has shifted. None of these effects individually would be disqualifying. Modern systems are designed with redundancy precisely because of this. But redundancy means margin, and margin means you are no longer operating at maximum precision. You are operating at acceptable precision, which is a different thing. There is also the compounding uncertainty problem. In orbital mechanics, errors do not simply add, they interact. A slight uncertainty in position combines with a slight uncertainty in velocity to produce an uncertainty in predicted future position that grows over time. Mathematically, this is captured in something called the covariance matrix, a mathematical structure that tracks how different sources of uncertainty correlate with each other. During a close approach, scientists are constantly updating this matrix as new observations come in. If individual measurements are noisier than usual due to ionospheric disturbance, particle hits, calibration drift, the covariance matrix does not shrink as fast as it would under ideal conditions. The prediction ellipse stays slightly larger. The size constraints remain slightly looser. This is the meaning of cascading uncertainty. Not catastrophic failure, not broken instruments, just the gradual accumulation of small imprecisions at a moment when you are trying to close the knowledge gap on an object of unknown mass, moving fast in a compressed observation window. The system is functioning. The system is stressed. And for 2026 DX6, both of those things are true at the same time. This next part is analytical modeling, not prediction. Let me say that plainly. The impact probability for 2026 DX6 during this pass is effectively zero. What follows is a structured thought experiment about coincidence and compounding pressure, the kind of scenario analysis that actual planetary defense teams run as a matter of routine. Not because they expect the worst, but because you cannot prepare for the unexpected unless you have already imagined it. Imagine the tracking precision for this object comes in slightly degraded, not catastrophically, but meaningfully, during the closest approach window due to ionospheric disturbance from the arriving CME. Imagine the radar cross-section measurement yields an ambiguous result because the return signal is noisier than ideal. Imagine the optical characterization does not resolve the albedo question because observing time at the key facilities was constrained. In that scenario, you exit the close approach of 2026 DX6, still not knowing its size to better than a factor of 3. You have an improved orbit, but the physical characterization remains a wide-open question. Now imagine this object has a future close approach, hypothetically years from now, and the long-term trajectory model requires knowing the Yarkovsky drift, which requires knowing the size. You would be carrying that uncertainty forward, not because anyone failed, because multiple small compounding stresses aligned on the same critical observation window. This is precisely how uncertainty compounds under simultaneous solar and observational pressure, not through catastrophic failure, but through margin erosion across multiple systems at once. The asteroid passes harmlessly. The knowledge gap persists longer than it needed to. And the next time this object comes around, whenever that is, you are working from a baseline that is slightly less precise than it could have been. That is the quiet, unsexy version of the risk, not explosion, information loss. Here is something that doesn't get covered in the asteroid headlines, and it should. The period of closest approach, the hours immediately surrounding the moment 2026 DX6 passes at 770,000 kilometers, is actually the most scientifically productive window of the entire encounter. Not because the risk is highest, it is not, but because the information density is highest. As an asteroid approaches Earth, its angular velocity across the sky increases dramatically. An object that moved a few arc seconds per hour when it was first discovered might be moving arc minutes per hour near closest approach. That rapid apparent motion across multiple observational baselines, different telescopes at different locations measuring the same object from different angles simultaneously, produces position measurements that constrain the orbit with extraordinary precision. Think of it as triangulation on steroids. The more the object moves against the background stars, the more leverage observers have to pin down where exactly it is in three-dimensional space. This is when the uncertainty ellipse collapses. What began as a broad, football-shaped region of possible positions shrinks over the course of hours into something almost pencil-thin. The orbital solution, the mathematical description of where this object has been and where it is going, locks in. And that solution, calculated during this 48-hour window, will serve as the foundation for every future trajectory prediction for years to come. Radar adds another dimension. During close approach, Doppler measurements of an asteroid's velocity become extraordinarily precise. The rate at which the return signal's frequency shifts tells you the velocity to a precision of centimeters per second. Combined with precise ranging, knowing the distance to within a few hundred meters, radar observations during close approach can constrain an orbit better in a single pass than months of optical tracking alone. If radar characterization is achieved during this encounter, the diameter question may also begin to resolve, because the radar cross-section of the return signal is related to the object's size and shape. It is not a perfect relationship and ambiguities remain, but it is significantly more information than brightness measurements alone. Post-flyby, albedo estimates may also be refined by studying how the object's brightness changes as it recedes and the phase angle shifts. Different surface compositions reflect sunlight differently at different angles, and the light curve data collected before and after closest approach can, given sufficient observations, narrow down the reflectivity range enough to tighten the size estimate meaningfully. What this means is that even though the asteroid is not dangerous, the 48 hours around March 2nd are not passive. Scientists are not simply watching something go by. They are collecting data under pressure, running real-time updates to orbital covariance models, and building the knowledge base that determines how we think about this object for the rest of its tracked lifetime. The story is not about the close shave. The story is about the quality of the knowledge we extract from it, and the fact that this particular extraction is happening during a geomagnetically active period, with the CME arriving in the same window, means the question of data quality is not academic. It is the actual operational variable that scientists are managing in real time. The planetary defense infrastructure is functioning. The redundancy is real, and the story of the next 48 hours is whether the margins hold. Let us step back for a moment and say something plainly, because this channel takes honesty seriously. 2026 DX6 is almost certainly going to pass harmlessly. The orbital data supports it. The tracking is consistent with a safe flyby. No credible scientist looking at the current data is losing sleep over imminent impact. That is the truth, and it deserves to be said without burying it in qualifiers. But the coverage around asteroids like this one, the headlines that use words like racing dangerously close and NASA warning, reflect something real about the gap between how scientists and how the public relate to cosmic proximity. When a scientist says 2 lunar distances, they are describing a measurement within a tracking system calibrated to find threats early. When a headline says dangerously close, it is translating that measurement through a framework built for emotional engagement. Neither is exactly wrong. Both are incomplete. The reality is that objects pass within lunar distance of Earth regularly, multiple times per year for catalogued objects, and likely more frequently for uncatalogued ones. Most of them are small and harmless. Some of them are discovered days in advance. A few are discovered after they have already passed. The catalogue of known near-Earth objects grows every year, which means the reported number of close approaches also grows every year, not because space is becoming more dangerous, but because we are getting better at looking. If you only started tracking pedestrians in a city last month, you would conclude there had been a dramatic increase in pedestrian traffic. The pedestrians were always there. What actually deserves attention, what the headlines rarely convey, is the tension between a detection system that is genuinely improving and a characterization pipeline that cannot always keep up. We are finding objects faster than we are understanding them. 2026 DX6 is a case study in exactly that gap. The orbit is known, the mass is not, and the real story of this event is not imminent danger. It is temporary uncertainty. A knowledge gap of the kind that the whole planetary defense enterprise is built to close, operating in conditions that make closing it harder than usual. That temporary uncertainty, concentrated in a 48-hour window, is the actual tension in this story. Not whether the rock hits us, it will not, but whether we learn enough from this encounter to do better on the next one. 2026 DX6 will be gone by March 3rd. Whatever the radar data shows, whatever the optical characterization yields, whatever size constraints we ultimately pin to this object, by this time next week it will be receding into the solar system at tens of thousands of kilometers per hour, and the news cycle will have moved on to something else entirely. A new headline will have taken its place, a new distraction will have captured the scroll, and 2026 DX6 will become a footnote in a catalogue that already contains tens of thousands of entries and grows longer every single month. But the questions this object raises are not going anywhere. And if you have watched this far, you already sense that the asteroid itself was never really the point. We are in a period of accelerating discovery. The near-Earth object catalogue grows by thousands of entries every year. Detection algorithms are improving, sky coverage is expanding, and the pipeline from raw telescope data to confirmed close approach alert is faster than it has ever been. Automated systems that once required human review for every flagged object now process detections in near real time, cross-referencing against known catalogues, calculating preliminary orbits, and issuing alerts within hours of a first observation. That is genuinely remarkable. A generation ago, something like 2026, DX6 might have been discovered the day after it passed, if at all. Today we had it tracked before closest approach. That is progress by any honest measure. But here is the part that does not make the press releases. The characterization pipeline, the part that takes a newly discovered dot of light and turns it into a known object with a diameter, a composition, a mass, and a reliable long-term trajectory, has not scaled at the same rate as discovery. Not even close. Discovery has outpaced understanding, and in planetary defense, an object you have found but do not understand is a partially solved problem, not a closed one. Finding it means you know something is there. Understanding it means you know what to do about it. Those are two completely different capabilities, and right now the gap between them is widening. Think about what understanding actually requires. It requires radar time at facilities that are shared across multiple scientific disciplines. It requires optical follow-up at telescopes that are already oversubscribed. It requires spectroscopic analysis to determine surface composition, which tells you something about interior structure and density. It requires light curve measurements over multiple rotations to determine spin rate, which affects how solar pressure acts on the object over time. Each of these is a separate observation campaign, requiring separate scheduling, separate expertise, and separate funding. For the thousands of newly catalogued objects added every year, only a fraction receive the full characterization treatment. The rest get an orbit and a magnitude estimate and a place in the database, waiting for a future observation window that may or may not come before the next close approach. This is where missions like DART become genuinely important as precedents, and not just for the obvious reason. In September 2022, NASA deliberately crashed a spacecraft called DART into an asteroid called Dimorphos and measurably changed its orbit. It worked. The orbital period of Dimorphos around its parent asteroid Didymos shortened by more than 30 minutes, significantly more than the mission's minimum success threshold. That was not just a headline, that was proof of concept for an entirely new domain of applied planetary science. The ability to deflect, to deliberately alter the trajectory of a natural object using kinetic impact, is now part of the real toolkit available to planetary defense planners. It is no longer theoretical. We did it. We measured it. It worked. But here is what that achievement actually requires in practice. Deflection requires lead time, years, ideally decades. A mission like DART needs to be designed, built, launched, and flown to its target before the threat window opens. That entire timeline assumes you knew the object was coming far enough in advance to act. And it requires knowing enough about the object, its mass, its composition, its internal cohesion, whether it is a solid rock or a loosely bound pile of rubble, to model the deflection effect accurately. A kinetic impactor hitting a solid monolithic asteroid behaves very differently from the same impactor hitting a rubble pile. The momentum transfer, the ejector dynamics, the resulting orbit change, all of it depends on physical properties we can only determine through characterization, which means every size estimate that remains a wide range instead of a confirmed number. Every composition that stays unknown, every albedo that goes unmeasured, represents a direct gap in the readiness chain. Not a theoretical gap. An operational one. Solar Cycle 25 is peaking right now, and it is doing so at precisely the same moment that our detection capabilities are more powerful than ever, and our characterization backlog is larger than ever. That is not a conspiracy. It is a coincidence with structural implications that deserve serious attention. More solar activity means more ionospheric disturbance. More ionospheric disturbance means more noise in radar measurements. More radar noise means slower resolution of size uncertainties during exactly the observation windows when we most need precision. And a growing catalogue of objects with unresolved characterization, objects we have found and filed and moved past, is the quiet, accumulating liability of a detection system that has been more successful than its downstream pipeline can fully absorb. We are filling the inbox faster than we are reading the emails. The next generation of survey infrastructure is going to make this more acute before it makes it better. Systems like the Vera C. Rubin Observatory in Chile, designed to survey the entire visible sky every few nights with extraordinary sensitivity, will accelerate discovery at a scale that is genuinely difficult to conceptualize. By some estimates, it will catalogue more near-Earth objects in its first few years of operation than have been found across the entire history of the field before it. Every few nights, the entire visible sky, objects down to magnitudes that current surveys routinely miss. That is an extraordinary scientific achievement and a characterization challenge of the first order. The objects Rubin finds will need follow-up. They will need radar time, spectroscopy, light curves, compositional analysis, and the facilities that provide those services are the same ones that are already operating at capacity today. The pipeline that is already behind is about to receive a flood. This is not a reason to slow discovery. It is a reason to invest in characterization infrastructure at the same rate we invest in detection. Space-based infrared survey missions, which can measure asteroid sizes directly from thermal emission rather than reflected light, eliminating the albedo ambiguity entirely. Dedicated characterization telescopes with guaranteed follow-up time for newly discovered close-approach objects. Faster international coordination protocols so that a discovery made in one hemisphere triggers observation resources in another within hours rather than days. These are not exotic proposals. They are the logical next steps for a planetary defense program that has genuinely succeeded at its first mission, finding things, and now needs to succeed at its second one. Understanding them. 2026 DX6 is not the story, ultimately. It is a single data point in a pattern that matters much more than any individual close approach. The pattern is this: we are getting better at finding things we do not fully understand, faster than we are getting better at understanding them, during a period of elevated solar activity that degrades our most precise measurement tools, at a moment when the gap between detection and characterization is already the widest it has ever been. That combination of factors, accelerating discovery, lagging characterization, solar maximum interference, compressed observation windows, is the actual diagnostic this weekend has handed us. Not panic, not imminent threat, a diagnostic, a systems-level stress test with a real object, in real conditions, on a real timeline. The asteroid is safe, the pass will happen, the data will be collected under whatever conditions the ionosphere provides, and the orbital solution will improve. 2026 DX6 will become a better understood object after March 2nd than it was before. That is how this is supposed to work. That is the system functioning, and we should acknowledge that before we acknowledge its limits. But here is the thought I want to leave you with, because I think it is the most honest thing this channel can say after a weekend like this one. Every close approach like 2026 DX6 is essentially the solar system presenting us with an exam we did not fully study for. It is asking us, how well do you actually know what is out there? And right now, in 2026, at the peak of solar cycle 25, with a detection catalogue growing faster than our ability to read it, with characterization pipelines under pressure, with radar measurements degraded by the same star that makes life on this planet possible, the answer is better than we did. But not as well as we need to be. Not for the ones we have found. And certainly not for the ones we have not found yet. The window was open for 48 hours. Scientists were watching, the instruments were running, the data came in, and somewhere on the other side of this close approach, we know a little more than we did before. Whether that increment of knowledge is enough, whether the margins we are working with are sufficient for the object that comes after this one, or the one after that, is a question the solar system will eventually answer for us. One flyby at a time.